Okay. Okay, today we are glad to have Professor Tanimoto, and he will talk about rational curves and Fano threefolds.
Okay, thank you. So thank you for the invitation and thank you for having me here. So my title is like rational curves on Fano threefolds. So this is joint work with Roya Beheshti, Brian Lehmann, and Eric Riedl. And then preprint is already on archive. So yeah. And then so I mean recently like we are studying like rational curves on Fano varieties from the perspective of Manin's conjecture. So Manin's conjecture is a conjecture asymptotic formula for the counting function of rational points on Fano varieties. And then with Brian, I mean, I have been studying geometry of Manin's conjecture. And then we realized that this study of geometry of Manin's conjecture can be used to understand the rational curves, space of rational curves on Fano varieties. And today I'd like to report some like recent progress on spatial rational curves on Fano threefolds. So this is something I'll talk about. So this is something inspired. So this is, I mean, techniques are algebraic geometry, but methods are inspired by arithmetic, like arithmetic geometry and the Manin's conjecture. So that's the idea of this talk. All right. So maybe then let me start here. So now, so introduction, preliminaries. So now let X be a smooth Fano variety over C. So that means that X is a smooth projective variety and then minus Kx is ample. So this is the Fano, definition of Fano. Then it has been proved by Mori that for any point on X, there exists some rational curve on X passing through that point. And in other words, so X is uniruled. So X is covered by rational curves, and the rational curve deforms a lot. And moreover, it proved by Koramio, Mori, and independent Campana that for any two general points x1 and x2, there exists rational curve connecting x1 and x2. So there's a rational curve connecting x1, I mean, passing through x1 and x2, and in other words, x is rationally connected. So these results show that Fano variety possess a lot of rational curves. So this is due to positivity of rational curves, and then these are proved using like a bend and break technique and so on. So it is natural to explore like a space of rational curves on smooth Fano varieties. What can we say about the space? I mean, how many components? What's the dimension? That's a sort of a question I like to ask. All right. So now which moduli space I'm talking about? So I'm talking about mainly like a coarse moduli space of stable maps of genus 0 on X. So so if you don't know about stable maps of genus 0, you can think of this is like a tree of rational curves. So like it's a union of rational curves, but there's no loop, like a union of P1, but there's no loop on genus 0 curve. And then we have like a map from this tree of rational curves to X. And then this is a nice thing about this space is like this is like so this projective, like each component is a projective scheme. And then, however, this gives a compactification of moduli space of rational curves on X. And then in general, so it is difficult to understand this space itself because some component of moduli space may generically parameterize reducible curves. So it doesn't need to be, each component doesn't need to be the compactification with reducible curves. It's possible that some of components generically parameterize reducible curves. And then, I mean, it's possible to analyze such a thing, but it's more like a that sort of thing is combinatorially more technical and complicated. So instead, we are interested in like lat bar X. So this is the union of component of a moduli space stable maps, such that those components are parameterized stable maps from irreducible domain. That means that it's P1. So basically, this is each component is compactification of morphism from P1 to X. Compactification of locus parameterizing P1 to X, but up to automorphism, yeah. But anyway, so we are interested in rational curves and its compactification. That's the idea. And then, so what should we ask about this modular space? So first question one can ask, for each component n of that bar x, what's the dimension n? And then does it coincide with expect dimension? So each component has has expect dimension. So I'll come to this point later, soon, later. But anyway, so one can ask whether it's coincide with expect dimension or not. In general, it doesn't. I mean, in general, it doesn't need to be equal to expect dimension, but in some nice situation, it does. And then, so I mean, one can ask when it happens. And if we understand the dimension, then next question is, what's the number of components parameterizing rational curves of anti-canonical degree less than or equal to d? So can we say something about asymptotics? So like we like to count the number of components parameterizing rational curves of degree less than d. And then, so, I mean, of course, these questions on itself are interesting, but the reason why I'm asking these questions are following. So the answer to these questions lead to the applications on, so geometric Manin's conjecture. So Manin's conjecture is about the simple formula for the counting function of rational points on Fano varieties. But then there's a version of Manin's conjecture for rational curves, like a space of rational, like a rational counting rational curves over finite fields and so on, so on. And then we are formulating with Brian. We have formulated some conjecture called geometric Manin conjecture, which basically predicts that for each algebraic class of like a algebraic class of curve, there's like a unique or not unique component we should count in Manin's conjecture. So this is called like a Manin's component. So in some sense, like a geometric Manin's conjecture predicts more or less like a there's some unique component for each algebraic class we should count in Manin's conjecture. And then, so we've been proving this conjecture for like some examples, like Fano threefold and so on. And also like this answer to this question has application to enumerativity of Gromov-Witten invariants. So Gromov-Witten invariants are very defined thing, but then so natural question is whether these, so even like a Gromov-Witten invariants are very defined, this invariant doesn't need to count actual number of curves satisfying like certain conditions. So actually, you need to prove that so Gromov-Witten invariance defined using like a moduli space or moduli stack of stable maps is it does coincide with like actual counting of number of rational curves satisfying certain condition, and this is so-called like enumerativity. So so answer to this question leads to like one can if we know answer to these questions, then one can prove like enumerativity of Gromov-Witten invariants. So these are application, but sorry, today I think I don't have time to explain these applications. But then, so yeah. Anyway, do you have any questions so far? All right. So then let me get to the smooth Fano threefold. So now from now I'm gonna assume that X is smooth Fano threefold. And then for each component of lat bar X, we have this dimension of M is greater than or equal to minus kx dot C, where C is a member of M. And then this lower bound is called, this minus kx dot C is called as expect dimension of M. And then this gives always a lower bound, but it doesn't need to coincide in general. But when it's coinciding, we say expect dimension is equal to the actual dimension. And then let me recall some definition of rational curves. Suppose we have a rational curve on X. That means P morphism from P1 to X. Then pullback of a tangent bundle is like so this is locally free C. So over P1, so it's split, so it can be expressed as a direct sum of line bundles. So you can have some integers A1, A2, A3, that's why these inequalities. and f star tx is given by this like direct sum. And then we say that this rational curve is free if a1 is non-negative. Otherwise, in other words, a1, a2, a3 all are non-negative. And we say rational curve is very free if a1 is greater than or equal to 1. That means that a1, a2, a3 all are greater than or equal to 1. So those are like a definition of free and very free. And then, so why we like this notion? Because I mean, so moduli obstruction is somehow when it's free, then obstruction moduli space vanishes. So in particular, like a moduli space, free rational curve is a smooth point of a moduli space of stable maps. And then, moreover, if you have like a component n generically parameterizes free rational curves, then evaluation map. So now M1, M upper 1, this is like a universal family. So this 0, 1 means that the genus 0 and with one marked point. So you can interpret this as some kind of universal family of rational curves. And then one can prove that if component parameterize free curves, then this evaluation map is dominant. And then dimension n is equal to the expected dimension. So dominant component is always has dimension equal to expected dimension. And then moreover, in general, if we have like a dominant family of rational curves, that means that the evaluation map is dominant. Then one can prove that general member of pi is a free rational curve. So this is something like one can follow from like a deformation theory. And I'm gonna use freely later. All right. So today I like to present improvement of Mori's bend and break lemma. So first let me explain what bend and break embedded in my Mori. So now suppose X is a projective variety, and suppose we have like a morphism from P1 to X, and then suppose that we deform F while fixing 2 points, X1 and X2, so that deformation sweeps out the surface. Then F degenerate to stable map G from C to X in the moduli space of stable maps, such that so C is a tree of rational curves because this is genus 0 stable map. And F consists of at least 2 non-contracted components, C1 and C2. And moreover, X1 is contained in image of C1, and X2 is contained in image of C2. So one can prove like this. So this is not exactly the statement of Mori's bend and break, but one can prove this from, by kind of analyzing Mori's proof. All right. So then this is a great lemma actually. This is super useful because there are so many applications of this technique, like a bend and break lemma, like a rational connectedness of smooth Fano varieties. Also like a boundedness of smooth Fano variety, first proved by using bend and break, like a bend and break technique, breaking rational curves. And then now Vilka proved like BAB conjecture boundedness of singular Fano varieties using like MMP, but originally like it is proved for smooth Fano varieties by Kora, Miyaoka, Mori, and then they use like a bend and break. Also like a cone theorem, Mori originally proves, this cone theorem using bend and break for smooth projective varieties. And then also like one can prove like the reducibility of spatial rational curves on Fano hypersurfaces started by Harris Ross Star, and then finally like also like a Riedl Young and so on so on. But Mori's bend and break has some issues too. That means that it is difficult to control the number of components of generation. There's no control a priori. There could be tons of components. And then also like a degeneration may be singular point of a moduli space. And then, this is a headache later on. If degeneration is smooth point, this is then we can use this, exploit this factor to do something, like to prove like a reducibility of space of rational curves. I'll come back to this point later. But anyway, so we like to have some kind of controlled bend and break, like somehow yeah, so that's something we want. So that, and then now our main theorem. So movable bend and break. So let X be a smooth Fano threefold, and let M be a component of lat by X generically parameterizes using free curves. And then suppose that general curve parameter M has anti-canonical degree greater than or equal to 6. Then M contains a stable map of the form F from Z to X, where Z has two components, exactly two components, and then restriction of F to each component realizes this component as a free rational curve on X. And then nice thing about this movable bend and break is that union of two free rational curves is a smooth point of M bar 00X. Yeah. So this is a really nice thing. What can exploit this structure, this fact to prove like a divisibility of spatial rational curves. All right. So that's one of our main theorem. All right. And then, so let me mention some application of this lemma, like a theorem. So now if you assume a movable bend and break, then Brian and I prove in like a previous paper that Batyrev's conjecture follows. If you prove movable bend and break, then Batyrev's conjecture is true. So what's Batyrev's conjecture? So in this case, so suppose like X is, so this is a theorem. So suppose X is smooth Fano threefold, then there's a polynomial PD such that number of components of lat bar X parameterizing rational curves of anti-canonical degree less than D is bounded by PD. So basically like a number of components is polynomial growth with respect to degree. So this is something we prove. And previous known bounds on number of components of Hilbert schema are sub-exponential. So this is a big improvement. But actually, geometric Manin's conjecture predicts something more stronger. Essentially, like, so this, degree of this polynomial should be given by Picard rank. That's more or less like a Manin's conjecture. Like not more or less, but that should follow from Manin's conjecture essentially. So we prove something weaker, but anyway, still like even proving polynomial growth is like a non-trivial fact, and then we prove using movable bend and break for Fano threefold. All right. So far that's the main theorem and the introduction. So far, do you have any question? All right. So
is the polynomial computable, that PD?
Sorry?
Is the polynomial computable, or is it just the existence of?
Right now existence, yeah. So hopefully, like if we assume geometric Manin's conjecture, then degree of this polynomial should be given by like Picard rank of X. So essentially, like if you, for example, if you assume that for each numerical class, there's a unique rational family of rational curves. If that's the case, then this should be Picard rank, right? Like, yeah. So, but our theorem doesn't give any specific growth or like a degree or so. Any information on it. Yeah. Okay. Right. And then our approach is inspired by Manin's conjecture. And then in particular, like our approach is central on Fujita invariant. So we use Fujita invariant. So let me introduce the Fujita invariant. So let X be a smooth projective variety over C. And then now let L be a big and NFQ a character divisor on X. Then Fujita invariant or A invariant of XL is minimum of real number T such that TL plus KX is pseudo-effective. Where now this effective upper one is like a pseudo-effective cone divisors. So if you don't know about pseudo-effectivity, then just think about this as effective, like a linear equivalence is effective. And then you replace minute by like a minimum, infimum. And then we know many things about this number, like this is a rational number, because L is a big enough. This is basically this is, I think, proved by Batyrev for threefold, and then in higher dimension by BCHM. And then also like by boson, demari, palm, pitane, A is positive if and only if X is in root. We know this. And also, formally, like, when L is not big, then we set A to be infinity. Yeah. And then so far we define this invariant for smooth projective variety, but I like to define this for singular variety. So now when X is singular, then we define this invariant by putting back to smooth resolution. So take a smooth resolution beta and then take a pullback and the invariant define A to be X tilde beta star L. And this is well defined because this invariant is a violation invariant under pullback of violation morphism between smooth projective varieties. So this is very defined. And then, so related invariant is first studied by like, I think Fujita under the name of Kodaira energy and so on. Yeah, so this is related to like a classification of polarized algebraic manifold and varieties and so on. Anyway. All right, so that's the invariant. And then, so this invariant plays central role in Manin's conjecture. So this invariant appears exponent of a simple formula in Manin's conjecture. And then, so also like so inspired by Manin's conjecture, we prove the following statement under the assumption of BAB conjecture, but the Hay-Conjam removes the condition on BAB conjecture. So after like Birka's first paper on BAB, Hay-Conjam made this theorem like unconditional. So now this is the Hay-Conjam theorem. So let me state that. So let X be a smooth unirooted projective variety, L be a big enough Q divisor on X, and let B be the union of subvarieties Y such that AYL is strictly greater than AXL. Then V is a proper closed subset. So in some sense, like if subvariety Y satisfies this inequality, then asymptotic formula for Y is bigger than asymptotic formula of X. So we should remove such a thing as an exceptional set. And then if you take a union, then one can prove that this is proper closed subset. And then this proof uses like a bounded system singular Fano variety, BAB conjecture, proved by Birka in essential way. I don't think we can prove this without having like a BAB right now. Yeah. All right. So then why this is interesting for rational curve? Because we have the following theorem. So let X be a smooth weak Fano variety. So minus Kx is big and F. And let B be the union of Y such that AY minus Kx is greater than X minus Kx, which is equal to 1. So now by Hay-Conjam's theorem, this is a proper closed subset. Then one can prove the following. Any component M parameterizing a non-dominant family of rational curves will parameterize rational curves containing B. So, in other words, any component M parameterizing rational curves outside of B is a dominant component. So once you component parameter rational curves outside of B, then evaluation must be dominant. So that means that its general member is free. So it has a dimension equal to expected dimension. So in some sense, like a dimension can be understood. Component of a dimension can be understood inductively. So first we compute this B, and then we analyze rational curves on B, and the other family of rational curves will be dominant components. So in some sense, like if you like to understand non-dominant family, then you only need to understand like a non-dominant family of rational curves on B. So this is very nice. All right. So then I'd like to say something more explicit about like these like a set B for Fano threefolds. And then so to do this, I need to recall like a Mori's classification of divisorial contraction for smooth threefold. So let xy fxy to be kx negative divisorial contraction from smooth threefold, and let E be the expression divisor on X. Then F and E are described by the one with the following thing. So E1, this is a blow up around smooth projective curve in Y, so Y is smooth. E2, F is a blow up at a smooth point of Y, so Y is smooth. and E3 F is blow up at a singular point, which is ordinary double point, and this polarized surface is isomorphic to smooth quadratic, where Q is smooth quadratic. And E4 F is blow up of singular point in Y, and then this polarized surface is isomorphic to quadratic cone. And then E5 F is blow up of singular point, and this like a polarized surface is isomorphic to P2 or 1. So these are like 4 types of contraction. And I really say that E has type E1, E2, E3, E4, or E5 according to the classification above. So anyway, like Mori gave the complete classification of divisorial contraction, and we will need this classification. All right. So now I like to analyze like a subvariety whose A invariant is bigger, strictly bigger than 1. So for example, for curve, it's easy. Let's trivial rational curve on N. Then we have SCL is equal to 2 over L dot C. So SC minus KX is greater than X minus KX, which is 1, if and only if minus KX dot C is equal to 1. So only rational curve we should consider here is like a minus KX lines. Right. So next question is surface. So let X be a smooth Fano threefold and Y be a surface satisfying that AY minus KX is strictly bigger than X minus KX, and take the resolution of singularity, and then phi be the composition of resolution of this resolution plus inclusion map to X. So phi is a map from smooth resolution to X. If this anti-canonical divisor, KY tilde minus AY minus KX phi star KX, this has the Ithaca dimension 1, then Y is swept out by minus KX lines. So that's the first case. And if equal to 0, then Y is a contractible divisor of E2, E1, E2, E3, E4, E5. Moreover, if Y has a type E1, that means that it's blow up of a smooth projective curve, then Y minus KX, this polarized surface, is isomorphic to quadratic surface. And then both rulings correspond to E1 contractions. So, I mean, this is not just E1, like E1 and both rulings are E1 contractions, such a quadratic surface. So in this way, like a subvariety of higher invariant are completely classified. So this is good. So then, so I like to have some application of this. So now let me focus on minus KX lines and then minus KX conics. So that means that it is rational curves of anti-canonical degree 1 or 2. So let X be a smooth Fano threefold. And then suppose that there's a family of minus KX line which has a dimension greater than equal to 1, strictly greater than 1. So now minus KX lines, expected dimension is 1. So this says that dimension of a family is strictly greater than expected dimension. So that's the assumption. Then these lines sweep out the contractible divisor Y of E5 type. Right. And then, so this is essentially known to Iskowski. I'm not sure he was aware for any smooth 103.4, but I think we have seen like he's claiming for like a smooth 103.4, such as minus KX is very ample or something. But essentially, this is known to Iskowski. But then let me give this proof of this lemma using A invariant. So, so we have a proof using A invariant. Let M be a component of Hilbert scheme parameterizing minus KX lines with now dimensions given by D. So we are assuming that this D is greater than, strictly greater than 1. Then since any minus KX line satisfy, so minus KX line, then A invariant is 2. So these line parameterize, line parameter M sweep out surface. And then by high conjunction theorem, resolution, if you take a resolution, then one can prove that this invariant of Y is greater than or equal to 2. On the other hand, by adjunction theory, surface whose invariant is strictly greater than 1 is classified. And one can give complete classification like P2, quadratic surface, and so on. So from that, one can conclude that A invariant is only possible. So only possible A invariants are 2 and 3. Right. And then suppose that it's 2 and take the resolution, and then L tilde will be a strict transform on general line. Then now this general line is covering family on Y tilde. So this is a nef free on Y tilde. So dimension D is equal to the expected dimension, which is given by this number. So this is the expected dimension of a family of a line on Y tilde. And then since L tilde is nef on Y tilde, so this is a moving curve, so it's nef. So in particular, we have, then this is pseudo-effective because the invariant is 2. So one can conclude that this invariant, this intersection number is non-negative, which is given by 1 minus d. Thus, this is a contradiction because we are assuming d is strictly bigger than 1. So our assumption implies that A invariant is 3, and the adjunction theory tells us that this is bilateral, this polarized surface is bilateral equivalent to P2O1, and then it must be adjoint digit. And then our theorem shows that Y is a contractive divisor, and it must have E5 type. So in this way, like you can describe like a surface suicidal line which moves a lot. Right, and then something similar for conics as well. This is also essentially known to Iskowski. So there's a family of minus kx conics which deform more than dimension, deform in dimension more than 2. So expected dimension is given by 2. So this moves more than expected. Then these conics sweep out contract divisor Y, which has a type E1, E3, E4, or E5. And then moreover, if Y has an E1 type, then this polarized surface is isomorphic to conic surface. And both rulings correspond to E1 contraction. So this is also proved by in similar way. Proof is more complicated, but then one can prove this using A invariants. All right. And then, so that's the subvarieties of higher invariants. Also, so one can analyze A covers. So suppose we have a generically finite dominant morphism from Y to X from smooth projective variety. And this is called as A cover if A invariants are same. So if you have like a generically finite dominant morphism, then by ramification formula, A invariant only can decreases. So this is, in general, it is already true that AY S star L is less than equal to AXL. But then when equal, we say it's A cover. And then this also plays like a central role in Manin's conjecture. And then one can classify this A cover so using three-dimensional MMP. So suppose we have like a smooth Fano threefold and the A cover, and suppose that adjoint divisor has Ithaca dimension 2. Then after applying resolution, we may assume that Ithaca vibration for this vibration is a morphism. And then general fiber of this morphism is essentially like a minus kx conic. Like a maps birationally to minus kx conic. So essentially, like if you have a cover whose adjoint divisor has a Ithaca dimension 2, then this is essentially a base change of family of conics. So in particular, like let C over M be the family of a component parameter in these conics. Then pi is birational equivalent to base change of P over some rational map from Z to N. And F factors rationally through the evaluation map for C. So essentially, like, it's base change of this family of conics. So that's the Ithaca dimension 2. Now, what about the Ithaca dimension 1? Suppose we have a cover whose Ithaca dimension is equal to 1. And then again, I'm assuming that after resolution, we assume the Ithaca vibration is a morphism. And then let YZ be the general fiber of pi and SZ be the image of YZ. So these are fiber. Then linear system SZ define the Delpes vibration. In particular, this cover is again base change so it's base change of this Delpes vibration. So birational to base change of Delpes vibration. So these are not so difficult to prove. These two theorems not so difficult to prove. And then last theorem is very technical. So now suppose we have a smooth Fano threefold, and then we are interested in a cover with Ijeka dimension 0. So adjoint divisor has Ijeka dimension 0. And then one can prove that there are no A covers such that adjoint divisor has Ijeka dimension 0. And the proof is intricate, very intricate, and then using like a 3-dimensional MMP. And then also like we have to use like Kawakita's numerical classification of terminal divisorial contractions. So here we use a lot of facts about 3-dimensional MMP, and then like 3-dimensional classifications and so on. All right. And then why we care about this? So this has some application to geometric rational, spatial rational curves. So this is the application. So let X be a smooth Fano threefold and M be a component, and let C be the corresponding component. C be the corresponding family, so component of M bar 0. So this is C is essentially universal family. And then suppose that evaluation map is dominant, but general fiber of this evaluation map is not irreducible. Then either M parameterized the family of stable map whose image is a minus kx conics, or M parameterized the family of curves contracted by derivative vibration. So I don't have time to explain this theorem, but this theorem is based on the following observation. Suppose we have a universal family and resolution, and take the Stein factorization of evaluation map. Then this Stein factorization, so Y is Stein factorization of evaluation map from C tilde to C to X. Then this Stein factorization is the A cover. So way to prove this, so we have family rational curves on X parametered by M, but then because it's factorized Y, this gives like a rational family rational curves on Y, and then both, and then they have like the same dimension and same expect dimension, which means that adjoint divisor is pseudo-effective, but not big. So that implies that the invariant is the same. So in this way, like one can prove that this is A cover. So, and then A cover is completely classified by those lemmas and theorems. So essentially, like, there's no adjoint like A cover whose adjoint divisor has Ijeka dimension 0. So essentially, only thing it factors through is like a family of conics, so like a family of derivative vibration. So mainly, like, that's the idea of this proof. And then this has some application later. Like, all right. So then let me, so I'm going to explain about proof of movable bend and break. Okay, so far, do you have any question? All right. Then, so then I need to prepare like one proposition, but I couldn't state this proposition in one slide, so it's going to be 2 slides to state proposition. Sorry, this is a mess. But now, suppose we have like a family of 1-dimensional general complete section of a big base point free linear series. So, okay. So this is a family of like a complete section, general complete section of big and base point free linear series, and 1-dimensional, each fiber is 1-dimensional. And let them be a component parameter stable maps that map birationally onto free curve of degree greater than or equal to 5. Okay. And then essentially one can prove that general member is of this component is like a local immersion. The stable map is local immersion. So one can think of a normal sheaf. And normal sheaf has like a expressed like this, OA plus OB. And A is less than or equal to B. And then we have like a 2, depends on this is equal to not. We consider the following like a configuration. So suppose A is strictly less than B, then consider closure T in M of all 1-dimensional components of sublocus of M, parameterizing curves in M which contain A plus 1 general points and it meets B minus A minus 1 general members of P. So somehow like So because of a normal sheaf looks like this, one can prove that curve contain A plus 1 general points and meet B minus A minus 1 general members of P. I mean, such a curve form like one-dimensional locus. And then we take the closure of this. That's the T. And then when A is equal to B, then we consider like a locus, closure of locus, parameter curves which contain A general points and they meet one general member of P. And then one can prove that again, like this curve satisfying this configuration form like a one-dimensional locus. And then we take the closure. All right. And then suppose that in this closure, we have a stable map F such that such that at least two components are free components. At least two free there are at least two free components. Domain Z with at least two free components. Then F must be one with the following thing. So either first case is D is a union of two P1s and both curve map birationally to free rational curve. Second, image of Z consists of a union of two disjoint free curves, and two disjoint free curves is connected by one minus kx line of E5 type, which connects the two free curves. And the third, image of Z consists of a union of free curves with two minus kx lines of E5 type. So like a two free curves, and then two minus like minus k lines, two minus k line connect them. So that's the situation. And then fourth, image of Z consists of union of free curves with a minus k conics of E1, E3, E4, or E5 type. So these one of them occurs. Moreover, in the case of cases 3 and 4 can only occur if A equal to B. And in these cases, one of the non-free curves must meet like a general member of P. So by looking at the configuration like this, one can prove that if we have like a breaking curve with like at least two free components, then either we have a union of two free rational curves, or like we have some free rational curves plus some E5 line, or like a minus kx conic of E5, E3, E4, or E5. So these are only things one can have. All right. So then, assuming, so I'm not going to prove this proposition, but then assuming this proposition, let me prove Movable Bend and Break. So proof of Movable Bend and Break is particularly easy when smooth Fano threefold doesn't admit any E5 contraction. So let me start that. So let X be a smooth Fano threefold without the E5 contraction. Then let M be a component generically parameterizing free rational curves. Suppose that curve parameter M has degree greater than or equal to 5. Then M contains a stable map from Z to X such that Z is a union of two P1s, and the restriction to both components of Z is free. Okay? And then proof goes like this. So first consider the contractive divisor of E3, E4 type or E1 type, which are isomorphic to P1 cross P1 with a normal boundary O minus 1, minus 1. So this is exactly like a chloric surface with both rulings correspond to E1 contraction. And then one can show that this is essentially known to like Mori Mukai. It's hidden there. Mori Mukai's paper, they basically show that these contractive divisors are disjoint. So one can prove that there's some birational map contracting all such divisors. Then now take the family of curves constructed by taking completed section pullback of very ample divisor on W. Then general member of P does not intersect any exceptional divisor of this like a contraction, right? Because this is based, and pullback of these things. So it's avoid like a codimension two loci. Then let X be T be the closure of one parameter family of curves as a proposition stated here. You got this configuration. Then Mori's bend and break essentially proves that T parameter is stable map such that at least two components meet pass through two general points. And then rational curve passing through general point is a free rational curve. One can show this. At least two components. So that means that this is a stable map with at least two components of Z. So now we need to apply proportion to stable map. So first of all, we are assuming there's no E5 contraction. So 2 and 5, 3 don't happen. 2 and 3 don't happen. And also like in the case of 4, one more non-free curves, namely minus kx conical E5, E1, E3, E4, or E5 type must meet member of P. But now P is avoiding general member of P is avoiding exceptional divisor. So 4 case also cannot happen. So it must be like a first case. That means that we have movable bend and break. So like I mean, so when so there's no E5 contraction, then it's easy. So next, let me discuss about like a E5 contraction when we have E5 contraction. So this is a statement. Suppose we have a smooth Fano threefold which admits E5 contraction. And let them be a component generically parameter and stable map that mapped bilaterally onto free curve in X. Suppose that curve parameterized by, curve parameter by M has degree greater than or equal to 6. Then MVB holds for M. So now note that when there's no E5 contraction, degree has to be greater than or equal to 5. But when we have E5 contraction, degree has to be greater than or equal to 6. And then proof is based on like a Mori-Mukai's classification. So but according to Mori-Mukai's classification, there are 6 types of Fano threefolds with E5 contraction. And then 5 of them admit unique E5 contraction. For these, one can apply the following proposition. Let X be a smooth Fano threefold with a unique divisor E of E5 type. Assume every free curve T of degree at most 4 satisfy E dot T is less than or equal to 1. Then MVB holds for all families of anti-canonical degree greater than or equal to 10. So this is proof is similar to like previous proof with the case of a proof without E5 contraction. Basically we use proposition. But then then let me not discuss about the proof of this proposition. But assuming this proposition for 5 of them with E5 contraction, proof is almost like by just checking low degree rational curves. So first I need to check this assumption is true for all 5 families. This is true. We check it. And then also like, so we prove for anti-canonical degree of greater than or equal to 10. So now we need to prove movable bend and break for anti-canonical degree of 6, 7, 8, 9. And this is done by hand. Like basically following classification and analyze these curves. And then we prove MBB theorem. Yeah. All right. Okay. So then now last thing. So there's a unique Fano threefold with two E5 contractions. And then let me discuss this example, and then I will end my talk. So now, what is it? Fano threefold with two E5 contraction. So this is blow up of the following projective bundle, blow up of projective bundle along quotic curve Z in a minimal moving section. And then we prove that there's a unique family of free curves representing each and every curve class alpha on X. So basically we prove like the divisibility of rational curves for each numerical class. And then we prove this by using movable bend and break. So we first prove movable bend and break, and then prove this theorem. So let me prove this theorem. So now E is the exception divisor for phi, and then E0 is a strict transform of rigid section of this projective bundle, and then infinity is a strict transform of D. Then E0 and the infinity, those are two E5 divisors. Now we have a projection to P2 and composition of phi with projective bundle. So now we have a composition of phi with projective bundle map, and then we denote by P, and then E prime this is the component of P inverse PE, which is different from E. So this is the consists of two components. And one is E, and another is E prime. Then another E prime is also like a contractible divisor, contracting of so contractible divisor of E1 type. And then contracting this yields a variety, this projective bundle in different way from phi. Okay. And then we look at the following numerical class of monoid. So first of all, like we have like a general 5 LP, and the R2 is a strict transform of line in minimal movable section, meeting Z in 2 points. R3 is a phi strict transform of general line in minimal moving section of this projective bundle. R4 is a crux construction analogous to R3 that use other bilateral contraction to projective bundle. So there's other construction of R4. So there are two contraction to projective bundle, and each gives like R3 and R4. And R5, this is the phi strict transform line in minimal movement section, meeting Z in 1 point. And then R6 is the class of construction analogous to R5 that use other bilateral contraction to projective bundle. Anyway, so you don't need to remember these. We have some curves. And then one can prove that these curves generate monoid, monoid of Neff curves. And then, so now let R be the commutative monoids generated by freely by these formal symbols, R1 to R6. And then we have natural numerical class homomorphism from R to Neff monoid. And then here the proposition, two elements in R are identified by homomorphism, this numerical to Neff monoid, if and only if they can be identified using like a sequence of following relation. So there are a bunch of relations between these generators. And then using these, taking quotient by these relation gives like a Neff monoid of curves. All right. So this is just like a computation. Yeah. And then now, okay, let me prove like a MBB for X. So this holds for at least degree 6. So we prove the claim for curves of degree at least 10 using induction. So low degree cases are handled by hand. So suppose MBB does not hold for some component that generically parameterized free curves in this degree range. Then, by proposition, we discuss here. So I don't think, so we don't have 4 and, so I think the only possibility here is going to be 2. So only possibility here is going to be 2. So at least if MBB doesn't hold, then it will contain point C1, LC1 parameter union of 2 free curves connected by line in E5 divisor. And then deformation theory tells us that stable mark corresponding to our broken curve is smooth point of M bar 00x. Thus, since this is smooth point, there's only unique component containing it. If this is containing the intersection of 2 components, it has to be singular point. So there has to be unique component. So this must be like original component. Then on the other hand, in most of the case, at least one of 2 free curves, say C1, will have a degree greater than or equal to 6. So by induction, this curve broke into the union of 2 free curves by induction, yielding like a C1 prime union C1 double prime union L union C2, and the C1 prime union C1 double prime is a general union of free curve obtained by applying movable bend and break to C1. And then again, this new curve is also smooth point of moduli space. And then we can smooth this part, C1 double prime LC2, and then resulting a stable map, it will be in our original component. And then this is like a free rational curve plus free rational curve. So movable bend and break is verified. So this is how we prove movable bend and break and smooth. So that's the idea. All right. So then now let me prove like this. There's a unique family of free curves representing any NF class. So we verify this statement for curves of degree less than or equal to 5 by hand. So low degree curves we need to handle by hand. And then also we prove each of R1 to R6 is represented by unique family MI. And since every NF class is the sum of these classes, we see that every NF class is represented by at least one family of free curves by just gluing and smoothing. There's at least one family of free curves. And on the other hand, let M be the set of components parameterizing free curves. And then by theorem about like A covers, this so wait a minute. This theorem about A cover, about A covers, so one can show that evaluation map for universal family for any component of M, any element of M, Pascal M, evaluation map for universal family over each component has irreducible general fibers. Okay, so has irreducible general fibers. Thus, if we identify two families of free curves on X, so then by gluing and smoothing, we can obtain unique component in it. So in some sense, like so idea is the following. Since general fiber, evaluation map of general fiber is irreducible, gluing component is irreducible, main component of gluing component is irreducible. So there's only unique component having this breaking curve. And then this means that M admits action of this R monoid. So M set of Pascal M admits structure of R module, where R action is given by gluing corresponding curve classes and smoothing. And then by movable bend and break, there's a surjective R module homomorphism from this guy to this. And this is surjective. And then moreover, two elements in R are identified by this numerical morphism, if and only if they can be identified using some sequence of relation we described before. And then we prove that for each relation, there's a unique family of rational curves of any of these classes. Thus, this surjection must factor through NF monoid of curves. In other words, there's at most one family representing any NF numerical class, finishing the proof of the claim. So this proof is something like we should hold in general. So, so one can, by using the theorem about A covers, one can prove like a well-defined action of a monoid. And then, basically MBB shows that I'm generating some, so these monoid is finite generated. And then by showing like a reducibility of low degree rational curve, of low degree numerical classes, one can prove that for each numerical class, there's at most one component. And in this way, like, so this is like something like, one can perform in general by going through classification, where we didn't do, but yeah, I think we have some, we are planning to let students work on some of the examples. All right. Thank you very much. So that's all.
Okay, thank you. Let's thank the speaker. Do anyone have any questions?
Sure, I have strange question.
Yes.
It's not exactly related, but it's kind of related. A lot of things which, a lot of objects which you use from time to time appears in different problems.
Oh, really?
Like say Fujita invariant and
Right.
other things, they appears naturally in different problems. So we've been working on Fano threefolds from a case stability point of view, which is absolutely different from. But a lot of things kind of similar. So, for example, did you ever met such thing in your studies? For example, if you take cone of not effective curves, but if you take a cone of effective divisors, for
Yes.
example, and you take, for example, anti-canonical divisor, and you take some effective divisor, and you start subtracting it until you hit the border of the cone of effective divisor. And then you take the volume of this guy, and then you integrate,
Integrate. Oh, so you are talking some kind of like a alpha invariant or something like that?
Yes, this is exactly beta invariant of Fujita and Akada. Yeah, but this is a kind of, maybe it appears also in Manin conjectures. No,
I see. Well, no,
I don't know.
never
I
see
don't
like
know.
a-
This is
maybe. Yeah, I don't know about this invariant very well, so I cannot say something intelligent. But yeah,
maybe consider this not as a question, but just a remark for the future.
Yeah,
If you
sure,
just
sure.
see this in number theory, this would be
Yeah.
great. Yeah,
yes,
something like that.
sure.
Okay. Any other questions? Okay. If not, okay, I would like to thank the speaker on behalf of everyone here. Okay.
Okay,
Thank
thank
you.
you.
Thank you. It was a good talk.
Yeah. So
Thank you. Thank you, Sho.
thank you. Yeah, thank you. Right.
Should I turn off stop the recording?
Yeah. I will upload the recording a bit later today. Yeah.